and I thought there's something wrong. So I decided to, was interested, I talked with some people, and I decided to do this. So the idea is, what I will start from nothing, and I will go on as at the speed that is needed. There is no restriction. You stop me when you need it, and I can pivot and change whenever you want. What is the goal? I will tell you in a second. Okay. So in the case, this is related to robots, this is much more general. This, I just change this sentence. So what is, robots are physical systems, and energy is the mathematical embodiment of an invariance of physical laws. Do you know what Noether theorem? Have you ever heard about that? Okay, Noether theorem is probably one of the biggest, most important theorem in the history of physics. Basically says that if you have a symmetry, you have a conserved quantity. That's roughly speaking what Noether was a genius of heliocentrism. It's called by Einstein and Hilbert as the most influential mathematicians lady in the 19th century. And Einstein didn't solve certain things thanks to Noether at a certain point. She came up with these results, which is at the basis of everything in physics, by the way. But she did a lot of other things. So this is an epsilon of what she did. And what that means is that if you have a symmetry, you have a conserved law. So what is a symmetry? What is energy? Well, we learn energy as engineer as being, something that, it's conserved, blah, blah, blah. But Noether tells you why. And the reason is if you have physical laws are invariant in time, there is a symmetry in time that results in a conserved quantity, which we call energy. And exactly the same is that if you have something which is, there's a symmetry motion in space, there is something which is called conservation of momenta. We all know that, but it's all based on Noether. And of course, this concept mathematically can be used in many, many different situations. Whenever you have a symmetry, you have a conserved quantity. So energy is really the mathematical embodiment of the invariance of physical laws. And physical interaction of robots with humans or the world is the core of many robotics applications. It's definitely, now there is in the past, robots were devices which were isolated and doing. But nowadays, a lot of important application of physical interaction, medical robotics, drones name it, it's clear. And yet, most of the time, energy is completely ignored in a lot of modeling ways of working, okay, and in robots. And so what I want to do is to give you an idea and a way to look into this in a port-based thinking, which is an extremely powerful, completely conceptually different way to do physics. Okay, I was just telling that Frederick Schuller, that is a fantastic mathematician. We are working happily now for 4 years. We are now moving to quantum physics. With him, I did a course in theoretical physics a couple of weeks ago in Germany, the top students of Germany. They were blown away about this, and they looked at as a relativistic situation using these concepts. Is conceptually different, and the idea is very simple. I'll try to convey that. So I will try to talk about a lot of things like, composition, openness, polymorphism, duality, topology, time delays, multiphysics. A lot of concepts will pop up, but we'll try to always structure in the mathematical formalism that is needed for that. And, Martin Luther King said, knowledge is a process of pulling up facts, wisdom lies in their simplification. Okay, and this is the core. Now, when I study something I'm very getting is mentally much more critical. If I do something, you should ask, why am I doing this? Sometimes engineers, especially, they learn to take steps without thinking what they do. But you should always be critical about why are the reason of that. And the most powerful thing that we have at our disposal is abstraction. Okay, to be able to conceptualize the things we do and reason on the level of conceptual reasoning. Okay, so I will talk about specifically a universal way to model physical system of any domain. You can talk about any domain, finite, infinite dimensional system, lumped or not. And this is general. And it turns out that amazingly enough, this stuff I'm really now working on specifically, that this stuff looks like it actually can formulate quantum field theory to a level that would allow things that have not been possible before. Okay, so it is conceptually very, very powerful and can interconnect different domains, and is very structurally related to Noether kind of concepts, etc., etc. Okay. Physical system has specific dynamic structure, and sometimes, very often, if you, especially from a mathematical point of view, you want to write to be generally say x dot is equal to f of x and y as a general dynamical system, okay, with a certain input to y, y, well, u I meant. Normally it's u, the input doesn't matter. But actually it turns out even that I have reasons to tell you that that equation doesn't make any sense, but we can discuss it during the break maybe, okay? And of course, less structure, you can give weaker results. If you have some structure you can use, you can say a lot about what you can do. And in fact, considering general nonlinear systems is too general to actually achieve results that will be possible if you use structure that describes that you are dealing with a physical system. Okay. This is just a video that everybody has seen this video. Yeah, so I can skip it. But if you haven't seen it, I'll show you. It's a very cool video. It's just as an introduction that I will show you later. For those who haven't seen it, I'll show you during the break. It's a very nice video. Okay. Well, then we skip. These are not relevant. These are other course things related to the course. These are not relevant for you. Not relevant for you. Well, this is a, okay, let's start from here. I strongly believe, and I always show this, the following picture that would be criticized that I don't pronounce it properly later. So to build a strong house, you need good bricks. And unfortunately, I am very critical about our education in many respects, but also in the way we actually teach our students mathematics. The linear algebra I had was actually decent, but I see it regularly that the linear algebra that is taught is actually bad. And I will give you reasons for this statement. I will build up and tell you why is that the case. Okay? So I will spend some time to tell you, to rephrase linear algebra in the way that actually makes sense for physical reasons, okay? And also geometrically. I always show this picture in all my talk. I love this Raffaello's painting, okay? What you read is Agiometricos medias isito. Is that good?
Good.
No.
Yeah? Yeah? He said yes.
Oh, said it okay?
Geometritos.
Agiometricos.
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 Yes, sorry, I had it wrong.
And because the Greek who had started philosophy is basically, considered geometry as something very important. But so it's not precisely what Plato meant with this sentence at the entrance of the academia, but still, I think that geometry still is something which is very, very important, and I will touch it again and again during the presentation. And I think that this is general. There's another thing I always show because it's very dear to me, is too often, good engineering means also to have good conceptual reason. So there is not only the engineering, what I would connect to the techne, but it's also the fact that, the reason, the episteme, the more reasoning abstract way is as important as practical stuff for engineers. And when you have a problem that you want to solve, you always have to translate it to your abstract world, to do a mathematical model, that you get rid of everything which is not relevant. That's the goal of the whole story. And then you do what you need to do and you transfer it again to the real system. And of course, philosophy, people like Kant have developed concepts of, what is an intuition, what are all these things. And that's the way actually as academic we should work. Another important genius of mathematics, Poincaré, said mathematics is the art of giving the same name to different things. What does that mean? That means that everything about abstraction, if you want to talk about the mechanics of a mass falling on the ground, you don't give a shit if it's blue or red, okay? it doesn't matter. So you should get rid of anything which is doesn't matter. So you want to find, and that's what mathematics does, at least if you use it properly in engineering, you want to distill what is really the structure you need in order to describe something you want to deal with. Okay. Far too often, a typical example I always say is, who of you have been told that a position is a vector? You don't dare to raise your hand, but I know you did. Okay. That is complete bullshit. How many times have you seen on books that vectors have a length? That's complete bullshit. Okay, this is wrong. There are books that students are given to students to teach, and they say vector space is the object that are called vectors, they have a length. It's not true. That's not what a vector space is. Okay, and why is position not a vector? Well, if I tell you Bologna and Enschede are two positions, right? Then what is the sum of Bologna plus Enschede? Doesn't make any sense. No, so it's not the vector. Position is not the vector. Because one of the things that vector do, they sum into each other and you can get another vector. So position is not a vector. If I give you velocities, that's a different story because they are vector indeed. Okay, so there are this bullshit that are spread around, conceptually completely wrong statements that I want to get rid of it. So, well, clearly stop me anytime. It's not the goal for me to talk. Is really to give you some conceptual understanding. Okay. Well, let me get rid of these things. I do think that this is really true. That we give. Okay. Now we go. So Einstein said true knowledge comes with deep understanding of a topic and its inner working. Okay, and that's the whole core of the way I want to teach you this kind of course. Okay, and Einstein, I don't know if you know, but Einstein actually, when he was at university, was actually a bad student. He did not follow a lot of classes. He was having fun with his friends. I don't remember the group of friends, etc. But he was very smart. And at a certain point, Grossman was, I think, was one of his friends. Who actually taught him differential geometry. And then at a certain point, this stuff is actually interesting. And thanks to that abstraction level that he managed to achieve by learning these things, was able to solve the problem we all know. Okay. Without that, he would have never been able to even cope with it. Okay. So what I want to talk is I want to start very, very basic. I know that for most of you, this is not necessary. But for the student, these are slides I use for the student. At least notation-wise, I want to be sure that at least we are on the same ground. Okay, so I will start from very start. Then I will try to build this up. But the important things that probably will do it today. We have how much time do we have today? Scheduled 2 hours, right? Okay, so it will be actually linear algebra. I think I will handle linear algebra stuff. Okay, so. I forget about this, it's not important. So let's go to sets. Okay. So this is something interesting to know. In 1900, there was a critical, very important point in history of mathematics, because there was this guy you may have heard, which was Cantor, okay, that started what is now called naive set theory. And then naive is for something I'll tell you in a moment. And in that time, he did not only do that, but it actually was the first guy who actually said, you know what? There are different kinds of infinities. Okay, they are countable infinities and not countable infinities. And he tried to formalize these things in a certain way. And some people like Poincaré say, well, you're crazy, you're nuts. Okay, and other people like Hilbert were like, oh, this is interesting. So there was a kind of split in mathematics in two groups. What are called the formalists, which Hilbert was the main exponent, and the intuitionists that were more like Poincaré and other guys. It was even Kronecker, another famous mathematician, who actually tried to boycott Cantor's career, mathematically speaking. So it was a big thing, okay? But nevertheless, in that time, set theory kind of was started by Cantor. And then at a certain point, Bernard Russell came up and Bernard Russell, a famous philosopher and mathematician, came up and came what is called a Russell's paradox, antinomy, that said, do consider the set of all sets that are not members of themselves. Have you ever heard about this? These are famous things in mathematics. And basically, you come to a paradox. You see that, it doesn't work out. You get that something is part of it or not part of it, so you get to a paradox. True is not true. True implies not true of something, so it's a paradox, okay? And therefore people say, oh shit, there's something wrong here. No, that's not what should happen in mathematics, that you have something that it's a paradox. So set theory was completely revisioned and formally described in a proper way. And that's the way Frederick does it on his course, by the way. And that's called the Zermelo-Fraenkel set theory, in which it's completely properly defined from a mathematical point of view. I will definitely not talk about that, but just it's important that you know that that is the case. Okay, so what you've learned about sets, that set are just things put together, is a very, very naive way of talking, which is good enough for us. But if you want to be precise, there's much more to be said, even for sets. Okay. So what sets roughly, I'm just, as I said, very roughly, a set is this is a notation. Where is it? This is a notation used. A is just an ensemble of elements. About definitions, there's this symbol that you find in some books. Sometimes if you define something, you define it. Some books you see this. Why this is bad? Any idea?
I think you said it before because
It's symmetric, right? So if I'm Arabic, is this A defined as B or is B is defined as A? I'm used to read from right to light or light to left. It does not tell you what. So the proper notation to create a symmetry. I mean, these are details, but are important details, right? So if I write it like this, I say A defined as B. Okay, so that's what is written there. And of course, there's, recognized symbols like Z, R, and R3 for the matrices. I think probably you have seen these things before, but these are just sets, okay? At least in these cases. Okay, and these are notations, so integer number is a Z, this pi is a rational number, this is an array of number, this is a matrix, etc., etc. Okay, and then once you have sets, then what you have maps. And what is maps? Well, maps is a map. So is something that if you give me an element in set A, associate an element in a set B. Okay, and A is called the domain, B is called the codomain. And the notation that is normally, and the beauty of mathematics, that doesn't matter if you are in Japan, in China, in Australia, in whatever place, is always like this. And notice the difference between this arrow. This means a map. And this means this element specific, which belongs to this set, is mapped to this element which belongs to this set. Okay, that's a notation. Now, maps can be, can start talking about what kind of maps. Maps is called surjective onto if it's, you have basically hits everything on the codomain. And this is for formal definition. It says, well, map is called surjective if for all B. So you take any element in the image in B. There exists an element in A, okay, such that that maps to B. So you basically get anything in B, there is one that maps to it. So you hit everything. Okay, that's surjective. Injective means that if you have two elements in A that are equal, they map to the same elements, that implies, okay, that they are the same. So you have no two elements that are distinctive that hits another element. And if they are surjective and injective, you call it bijective, means it's 1-to-1. Okay. And these symbols, you also have probably seen this implication. You can properly define it. And theorem is basically a theorem in mathematics is something like this. This is a logic thing. This is a logic thing. This is a hypothesis and a thesis. Okay, the theorem is this an expression of a theorem. This is a necessary condition for this. This is a sufficient condition for that. Okay, and if this is a if and only if, it goes in both directions. And once you want to prove this theorem, you start from here and you can deduce that this is true. Once A is true, you prove it in the standard way. But it's also true that if this is the case, automatically you have, but the pen doesn't work. You have that. If this is not true, because these are logic statements, this implies that A is not true. So if you want to prove these theorems and you do it this way, it's called a proof by contradiction. Okay? Okay, now we start about structures. What is a structure of a set? Okay, now now we go to Poincaré. Well, Poincaré, what we want to give the same name to different things. What is the bare things that a set tells you? Okay, the only thing that the set has is one thing, is cardinality. No other information. Okay, if I give you the elements of the set are 3 elements, I can call them A, B, and C, or pear, apples, and chair. It does not matter. Okay, they are the same thing. It's 3 elements. So if I have now a map that maps from one set to another set, what is the map that's preserved the structure that mathematical object has? Well, the only thing it has is its number of the number it has. So a structure preserving map or sets is called a bijection, 1-to-1. So you have one element here associated to one element here and the other way around. Okay, that's a structure preserving map for sets. And that's one. So you have a set, you have a Cartesian product. So if I have a Cartesian product, means I have an element set in A and I have an element set in B. I can consider all pairs, okay, from A and B, and that's the way you write it. Okay, that's a Cartesian product. This is just notation. This is an example. Any questions so far? These things you have seen before, just notation, okay? Now we go to group. Group is a mathematical structure which is fundamentally important, okay? And in fact, you know, group is the simple structure, algebraic structure you can think of, okay? And then if you allow the structure, you get to fields. What are fields? Fields, I mean here fields, not vector fields. Okay, fields are like real numbers is a field. And it can be defined, of course, properly. Complex numbers is a field. And you can go, I think, in FIFO algebra to other kind of more generalized fields. But the fields which make sense, definitely in engineering, are real numbers and complex numbers, okay? In everything we do in robotics, for example, we only deal with real fields. If you do quantum mechanics, you only deal with complex fields, and there are reasons for that. So there are here just 2 places where you can look at these 2 things on groups. Is very nice. Actually, are very simple, well-prepared videos that explain in more intuitive way what groups are. And I can share the slides also with you for the Q code. Okay, but this is very, you know, you definitely know 3 blue, 1 brown is my hero. Is this guy is fantastic. It's just amazing. And Socratica is I think I don't know if she's a mathematician or an actor, but in any case, the course is well done. Okay, but this guy is phenomenal. All right, so what is a group? Now we have a set. So we want to do algebra. What does that mean? Well, it means that you want something that you can do operation with this. Okay, so, but there's nothing else in mathematics than maps. If you have sets, you have sets and maps. So what can we do if you want to do operation? Well, we define a map that takes 2 elements from the sets we are dealing with, and it spits out an element there. So if you define that map, you know, if you take these 2 things, that will be the result. And I can use a different notation, okay, because I can say, well, I define this object as the application of that map to A and B. That's the formal way you would write, for example, addition, sums, or things like that, okay? But the sum, addition, and all this is just a function, okay? All right, now what is a group? Well, a group is a pair, are 2 things. It's the set which it's formed and the operation on that set that should satisfy a number of things. The first one is what it calls associativity. That means this function eats only 2 things. So it cannot handle, in principle, 3 things at the same time. But if you want to do something with 3 things, you can feed them first the first 2, you get 1, and then you do with the result the other one. Okay, and associativity basically tell you, well, it doesn't matter in what order you do. You can first feed M1 and M2, you get an element, and then you feed that with M3 again to the function, or you take first M2 and M3, you feed it then. Okay, that's called associativity. Okay, and then you have identity. It means that set is special. There is a guy who is the king of the set, so to speak. Okay, we call it the identity. Okay, and the identity basically says, this rule says, you know, there is a very special guy there, or girl, okay, in which you have, if you take any element here, and you take this special guy, which we call the identity, okay, if I take the operation between whatever element you get and this special thing, or the opposite orientation, I always go to the same element. Okay. Now, if I tell you that the set would be integer, and the sum would be, excuse me, and the operation would be sum of two integer, what is the identity element? Right, because whatever element you take, 0 plus any number is give you that number, okay? And if I give you now instead real numbers, and I tell you the operation is product, and I should be careful about the details there, what would be the identity element? 1, okay? And then you need to be careful, of course, there's centination. Okay, if I give you now a set of square matrices, okay? Then, and I ask you the same question, what would be the identity element of that set of square matrices? The identity matrix. It's clear, right? Okay. Then you have another thing. You have the inverse. This is the last thing you need for a set. And this means that, you know what? If I give you whatever element, okay, then there should be, if it's a group, there should be another element in the set such that if you take the pairing with these two guys, you give the, excuse me, you give the identity. Okay. Now, let's go to the example before. What is the inverse in the first case? I say integer with the sum of plus 3 minus 3. Right. So it's clear. And if you have an irrational number of let's say 3, it would be 1/3. Clear, right? Now, you have to, what is a necessary condition, something you should be a bit careful in the real numbers? Can I do it with all real numbers?
But every number, every element of the set is invertible. So there should be no 0.
Exactly, it's clear, right? So you don't want to have 0 there. Okay, because so it does not work for all real numbers. Should be all real numbers, but you should first get rid of the 0, and then you have a group. Otherwise, it's not a group. Okay, because there is something that cannot be inverted, so it's not a group. So the real numbers are true. Then, if you get rid of the identity, and for matrices, what should I take care of? Can I take any square matrix?
I cannot take the 0.
Yeah, but are there more than that?
Again, it has
So that has to
full rank. Yeah.
It needs to be invertible, right? So in fact, the group, which is the most general group of matrices, is sometimes indicated as GLN, called the general linear group of dimension n. Right? And of course, this is more general than the matrix, so this, I should be careful. But basically, what this is roughly speaking, a set of n by n matrices which have no determined difference than 0. Okay, that's the biggest group that you can represent in matrix space, kind of stuff. Okay, and if you restrict it further, you have different other things, subgroups that you also talk about, and we'll see them. Okay. So that's what the group is. Well, these are the example, and this is real number with operation this, but then you have to take here not matrix with matrix product operation, object motion. So you see, now you should start appreciating the abstraction, right? Because now that concept can be applied to much more than the number you're used to. Because if I give you now motions, I can talk about, you know, something that acts on this body, and we'll see it again and again. Okay, so I can say, well, if a group acts on this like this, okay, so all possible motion from there can be represented by an element in the group. What would be, if I do this, what would be the inverse of that? Would be this, right? Because if I do this, and I can go backward. Okay, so you have the motion that you apply, there is an inverse. What would be the identity there? No motion, right? And no motion, in fact, is the of this motion and this motion, right? And you can indeed, the operation is composition of motion, because I can have a motion like this and a motion like that. Okay. And is it the same if I invert the two? No, I didn't say anything about what is called commutativity. There is no property in the group, right? So a group is abelian or commutative if also an extra condition is that if you take the operation like this, is always the same as like this, okay? So additions and multiplication, of course, are commutative, not of matrices. And in fact, another interesting anecdote of historical anecdote, you ever heard about the guy called Heisenberg, I suppose, right? Well, this is precisely what happened when he went to Helgoland, the famous time when he was, basically came up with the basic idea about quantum mechanics. At a certain point, he realized that he was looking at atoms and change of level, and there was something which was not commutative. Depending on the order you did certain things, you got different results. And then went to Max Bohr, and it was saying, there is this thing. It says, well, there is something that engineers use. They are called matrices, and they are not commutative. Maybe you should look into it. Not a joke. This is precisely what happened, and that was the start of what is called matrix mechanics, okay, which formed the basis of quantum mechanics, which is well known for the fact that it is not commutative for indeterminacy principle of Heisenberg. Okay,
But for a set to be a group, commutativity is not needed.
well, a set is not a group is two things: a set and the operation.
The previous
So
was just
a
characteristic.
set is not a set. A group is more than a set. It's two objects. It's a pair. It's a set and it's an operation. You cannot see them separate. So if I give you a set and I don't tell you that there is an operation, it's a set. It's not a group. If I give you matrices and I don't tell you that you can multiply because I don't give you the it's just a set of matrices.
So for a group, there are certain characteristics depending on the group,
Depending on how you define the operation. And then you can check whether that operation is indeed abelian, invertible or not. Okay, if it is for all possible cases, of course, not only for a few, and you can have groups that, certain things, and then you have the whole theory of about this stuff. But if you can always invert, that means that is abelian. It is invertible. Okay, any other questions?
Can I read the second example without zero?
Should, yeah, absolutely. Let me, yeah, absolutely. Yeah. Any other questions? Okay. Now, so these are some examples, and I will talk about quaternions. Quaternions are very, very well known in robotics, and they actually are isomorphic. I tell you what that means to another complex group, which is ICU2, unitary group of order 2, which is the basis of, for example, quantum bits and quantum mechanics, which is a complex group. So you see there are different representation of the same mathematical thing. And that's important in the abstract. So they are the same thing. Okay, now what is the structure of the group? So, I had a set. Well, we say if I have two groups, I give you two groups, and it means that I have a map that preserves the operation. I'll tell you what that means in a moment. We call it a homomorphism. Okay, so you see, depending on the structure that you have, if you have a map that preserves that structure, okay, it's called the structure preserving map for that mathematical object you're dealing with. For a set, the only thing you can do is count the numbers. But if I give you a group, you have operations. So you want that if you do operation here and you map the elements on the side, you do the same results. So this is the definition of a homomorphism. Obvious. There is no other way. So I could have, let's go back. What is the definition of a homomorphism? Try to tell me. I have a map, which is a group. On the left, a group means it's a set and an operation. I indicate it like this, okay? Then I have a map. That map basically elements here, two elements, let's call it M. I don't know how I call in this slide, star. That's the other operation, okay? And I want that this map that maps these elements here is also preserving the structure, the operation. How would you define it? So what can we do? We can do an operation here, right?
It was defined it as there is a one-to-one correspondence with every element of the third set to the second set. So
No,
that
that's not needed. One-to-one is not needed. Is not needed. So what can we do? The structure is the operation, okay? Let's look at that. We can take two elements here, right? Let's take A and B in G. Okay, and we do an operation. So what do we get? We say A, B, suppose you get C. Now, what can you do now? You have three elements and you have a map. What can you do? You can map them there, right? Okay, so what do you get? Here you would get, let's call this F. Okay, you would get F of A, F of B, and F of C. Now, give me a condition that preserves the operation.
that the transfer of E.
Clear, right? So what you say is, what you want is that this operation is a different operation, right? So what you want is that F of A with this operation, because we are now on the right side, with F of B, okay, is equal to this. You have no other choice. You see how logical that is? So why is this so, why am I stressing this so much? If you have the right structure, the right details, this is a fundamental, simple thing. It guides you. You know what you're going to do. This is something I'm realizing daily, okay? On the stuff I did in Portwings, in mathematics, at a certain point, the mathematics tells you what is right and what is wrong. Typical example, at level 0, if you do any basic physics, what you always check first? Units. You know that if the units do not work, the rest is for sure bad. Okay. Now let's lift it a little higher at a certain point. You will learn this. If I do matrix multiplication, you know nothing. It's bullshit, just matrix multiplication. But if you then know what those matrices are, and we'll see what actually matrices are, because they are not mathematical objects, okay, then you know if you can multiply this with this, makes any sense. That was the way that has been guiding a lot of development in general relativity, the tensor calculus. And what my work is now I'm putting in physics and putting forms, which is another kind of way of looking, when you really see what integration is. Because a lot of things in physics is about integrating stuff. And a lot of people, physicists, they integrate things without realizing what integration is. By using coordinates, and they lose what's going on. That was the guiding line on Portwings. We will see all these things. But you see this point? You see, it's obvious that once you know the structure, what the map should preserve that, right? Yes, please.
Is it an example of what we were describing here? If I take roll, pitch, and yaw, and I say that summation is the operation. Yeah. And in the other, and then there would be a map that would go to rotation matrices and multiplication.
You have to be careful because, there are tricky things about singularities. Locally would be an homomorphism for sure, but you have to be careful. Okay. So we'll look at these kind of things, but that's exactly the kind of, I give you an example which is even clearer than that. But for Vincent, you see, I didn't say anything about bijectivity. I didn't say that because, as a group, they do not need to be bijective. This could be much smaller than the other one. No problem. There are many examples for that. Yes.
So, I mean, I agree, right? But but I'd like to hear from you. Can you explain why that part of the structure doesn't have to be preserved? So we're talking about structure preserving maps.
Yeah.
You preserve the product, but you don't care about the cardinality.
Very good point. Very good point. Because because I think this is something related to category theory. Okay, that's as you know, I'm interested in it. I have not. I'm definitely not proficient enough to give you a proper answer to that. But what I think is going on is the core of the structure you want to deal is functorially speaking, is a term in category theory, is the operation, is the algebraic nature, is not the cardinality. Because if you have something which is a group homomorphism and would be at the same cardinality, okay, and very likely would be that bijective automatically, likely it would. I should think about it.
Difficult with infinite groups, but yeah.
It's difficult with infinite group, but let's stay to finite group. I think then you automatically would have then it's the same thing. Now, if you give it two sets, okay, and you want to preserve the only thing of the sets, you don't have redundancy in some sense, right? Because that's the only thing you can preserve, and automatically they would be the same thing, and isomorphic. But here you already have extra structure in which you want to concentrate the preservation, and that's the group operation. That I think is what is going on.
Are the morphisms of sets bijective maps, or are they just maps?
You cannot talk about. I mean, you mean by the
In the category of sets.
yes. I mean, you could define
Yeah.
any map which is not a bijection, right? But it does not preserve the only structure that you have. That's what I mean.
Yeah. I mean, it preserves an order of cardinality. In sort of the same way this does, right? You can't create a bigger group.
Yeah. Okay. Yes, it could be the case, but I think that's should be looked in the category theoretical context, which goes a bit further than what we should. But that's an interesting question to be looked at. But the concept is that in any case, probably the set should be look at how it is done in categories here, but it is definitely correct. Okay, that you preserve the operation, and we'll see a much even more interesting things for engineering in a moment, which is, and I'm building it up because I want to show you that is a kind of always the same story. Now look at this. This is very simple group homomorphism we use all the time, right? You go from oh no, sorry. This is the definition which we have seen. Okay. And now an example is this. You use it all the time. Okay. If I give you the set of numbers and you take the sum and that one side, and then you take the exponential as the map, then you get the product of the result on the other side. Simple as that, right? Okay. And you know that if you restrict the domains properly, then you have a bijection there. So it does not really matter what you do on one side or on the other. And in fact, if you know something about information theory, Shannon and these kind of things, this is precisely what's going on in probability theory. Because the information would be the elements on the left, okay, and the probability would be on the right. And there is a bijection between information and probability. And this is the guy. There is an isomorphism between probability and information theory, okay? So it is the same, but it's very, very useful. We use it all the time, right? Sometimes this fact that one multiplication, logarithmic scale, and all these kind of things, we use it all the time. Okay. This is nothing else than a homomorphism. All right, now we get to something important. Linear algebra, things that you think you know, and the first question is, do you know what matrices are? And everybody says, yes. And I'll show you don't. Okay. Let's play a game. Have I played this game with you already or not? With you, probably.
Yeah,
yes, I did. Okay.
Not all of us.
Okay. So this is more for the people that never seen, because I love these slides. So you know these two guys. So the one on the right is, I mentioned it before, was David Hilbert. Probably the biggest mathematicians exist in the 19th century. Okay. He basically was the founder of functional analysis. He was the guy who helped Albert Einstein to come to what is called the Hilbert-Einstein action, and in which there have been a historical dispute to who was first to find it, to get general relativity, which is basically the action that results in Einstein field equations. So a genius, absolutely genius. The guy genius than the guy on the right. That is John von Neumann. If you have a computer, you know his name because of phenomenal architecture. He made basically the whole conceptual concept about computers. He basically builds all the mathematics on operators, which is needed for quantum mechanics from the very scratch. And he was not stupid, okay? And he was, by the way, a student of Hilbert, so he spent some time with Hilbert. And there is a nice historical anecdote one in the conference, have you ever heard about the Hilbert's problems? At a certain point, Hilbert put a number of problems and for the mathematics of those time after the 1900 crisis I mentioned before. And then he said, one of the problem was consistency of the mathematical settings. So they have axiom, can always create any axiomatic settings in a consistent way. And at that very conference, Van Neumann was actually not following the talk of Hilbert 2 days before. It was at the presentation of a guy called Gödel, who actually presented a paper who actually showed that what Hilbert was trying to do was not possible. Okay, so there are a lot of this anecdote. But anyway, these two guys know about matrices. Okay, now these two guys are given the simple matrix which is given there, but one is red and one is blue. Okay, so are numerically the same thing, but they have a different color. And then they are very far from each other. And I asked to John Van Neumann, to Hilbert separately to do certain things. I asked, make a square of that matrix. Van Neumann makes the square, calculate it. And then I asked Hilbert, and Hilbert said, come on, give me a break. It's not defined. I can't do that. And he knows how to multiply numbers. So he's Hilbert. Okay. Huh? What's going on? He's right. He's absolutely fundamentally right. But he doesn't want to do it. Then I ask the inverse, and then Van Neumann says, "Oh, no problem. I just do it." And then Hilbert said, oh, "Come on, I can't do it, but I have to change the color." What's going on here? And then I go to transpose, and I say, "Well, I can't transpose it for you, but I have to change the color." Okay. And Hilbert transpose it doesn't change the color this time. What is going on here? Well, it can get worse. Let's go to something called eigenvalues. John, can you calculate the eigenvalues? Sure, no problem. David, can you calculate the eigenvalue? Don't give me a break. I can't calculate the eigenvalue of that matrix. And he knows how to do operations on numbers. Okay. They are both right. What is going on here? If I give you a matrix, and I ask you to calculate the eigenvalue as an engineer, and unfortunately as a mathematician very often, because it is an effect that Fredrik told me that certain people in mathematics do not want to teach you what I will teach you. Okay, they would just calculate the eigenvalue. It makes no sense. Not even why. Okay? You can calculate it of that matrix as numbers, but mumbo jumbo. You can calculate it, and that is what Van Neumann would give you eigenvalues. Okay, but as a physical representation of something that would make sense from a physical point of view, it doesn't make sense. I'll show you. And then I asked the determinant. Van Neumann calculated the determinant. Hilbert says bullshit. Then is change the base. Then maybe you see what's going on, because Van Neumann showing change in basis by putting on the right side, on the left side. Of course, an inverse, and the other one put a transpose. That is something stinking, because these here, you see, they do not change coordinates in the same way. When do they change coordinates in the same way? When S inverse is equal to S transpose. When is that the case? I know you know, but the others should try.
Orthogonal. Orthogonal.
Well, you have an orthogonal, but why would you choose that? If I change, any coordinates change could be fine. I mean, if you restrict yourself to only those coordinate change, and you were very clear from the start, fine. But as an engineer, have you ever used polar coordinates? Sometimes. If you look at motors or PQ decomposition, I mean, it can happen. Okay, as a robotics is not much, but if you actually change coordinates of twist, we'll get to that. You always have things which are not orthogonal. So also in robotics is not unusual. So you should look at what are the right things to talk about these things, right? So what is going on here? Now, what is going on, and you will understand in more detail later, is this. The first one is a linear operator. So it's a map, which I will define properly. It's a linear map that goes from a vector space to itself. is what is called an automorphism. Okay. The second one is a quadratic form. Can you give me an example of what that may be? In a physical case. So if, for example, if V would be representing velocities, what?
Energy.
Kinetic energy, right? Co-energy, I should say. So if you have you have quadratic form, you have V transpose. So we would have, let's say, the half. Forget about the half. You'll be V transpose and V, something like that, right? So these elements are velocities, both velocities. Have you ever seen somebody calculate the eigenvalue of an inertial matrix? Yes. Bullshit. Complete, absurd bullshit. It makes no sense. I'll show you that. It makes no sense. Why does it make sense? Can you give me a reason? Kinetic energy is something, it's a scalar, right? It's a physical thing that under certain observed condition does not change. Okay. Now, what happens? How do I change the coordinate of this? How do I change the coordinate of this object M? Suppose I change the coordinates of V. And you see immediately that you have a matrix on the right and a transpose on the left. Clear, right? Not in inverse, a transpose, because there's a transpose here. Okay. Now, if I calculate the eigenvalue of a matrix, you have certainly seen that. When is that invariant? When you multiply it on the right and on the left for a matrix, and it's inverse, not its transpose. So if I calculate the eigenvalue of M, and then I change coordinates, okay, with the transpose, the way it should be changed, and then recalculate the eigenvalues, you get different numbers. Try an example. So what the fuck is, excuse me the word, what is the eigenvalue then? It's a completely arbitrary thing, because I could even find a change of coordinates that give me the eigenvalue that you want to have. So to take eigenvalue of an inertial matrix makes no sense. Full stop. And I will convince you about it later even better. Okay, this is just to warm you up. But what is the definition of an eigenvalue?
At least following 3 blue 1 brown, as far as I remember, the change of the unit vectors before and after the operation.
It doesn't have to be a unit vector at all, but it's more or less that. Okay, so you have, well, if I give you a matrix now, let's call it matrix, we'll see what that object is. Okay, and I multiply it by a vector. So this is something that maps this to something. This should be equal to, that's the equation we use, to what? To lambda, which we call eigenvalue, and V. That's the equation. And nota bene, these things is very general, because now A, we'll see, this could be infinite dimensional. You know, this doesn't have to be a matrix. This is a linear operator in general context. But what you see immediately is, if I take this vector, this element belongs in V, right? So this V belongs in V. So this belongs in V. Where does this belong? What is the set it belongs to?
Range of V.
Eh?
That's a range of A.
Yeah, but as an element. As an element, you know, I take an act in V and multiply it by a scalar. Where does that belong?
Vector space.
In V. That's one of the operation of a vector space, right? So if I take a vector, I multiply, that's it's one of the operation of a vector space. We'll see all these details. Okay. So this is in V, right? So it makes sense to calculate the eigenvalues only if this A is what kind of thing? It's something that maps something in V to something in V. And M is not a guy like that. M is the guy like that. It's a different thing. What M does, we'll see this, is something that maps elements in V to elements somewhere else. What is this in mechanics? If I give you a mass and I multiply it with velocity, what do I get? A momentum. Very good. Is this belonging to the same space as V? No. They told you maybe yes, but it's no. Okay? And I tell you why. What is Newton's law? The proper wave formulation of Newton's law, which always works. Second law, I mean.
Rate of change of momenti.
Very good. That's Newton's law. Okay? So, if I give you something in a space, which would be a vector space, but it's not V, and I take its time derivative, where would it belong? It stays there, right? It does not change where it is. You look at the variation in that space, roughly speaking. I will be more precise, but I just want to build your intuition. So it means that F is in the same space as P. All right? Now, what is power? How do you calculate power? If I give you a force and a velocity, how do you calculate power? Force, I'm writing like this as a row vector, times velocity. That is power. Now I ask you, if I change coordinates, okay, you calculated power in your whatever coordinate, you calculated power in whatever coordinate. Is it normal that you get different results? Definitely not. Energy may be the case, power does not have to be the case. Because power is even deeper than energy in that respect. Well, it turns out that this guy, the way to properly talk about this guy, we'll see this precisely, is not a vector. This guy is a linear operator from vectors which are here to scalars. And I'll show you that these are not the same guys. Okay, so forces are dual to velocities, are not belonging to V. That you were told that, wrong. Are belonging to something which I properly defined, which is called V star, is the space of linear operator from V to R. Okay, that is why here this guy is conceptually, intrinsically, physically different than this guy. I can take eigenvalue of this, I cannot take eigenvalue of that. If I have a linear operator, I can take the square. What is the square? I take that operation and I take it again. That's what it is, right? If I take a square, it means I do an operation, I do it again. So if I have a map from V to V, I'm left with something in V. So if I apply it again, no problem, I have the square. But if I have a map like M that goes from V to V star, and I want have the map that goes from V to V star, I can't use it because I get something in V star. It's a different thing. You get the feeling? Okay, so that is a different thing. That's why you can take that and you cannot do that. Once again, I will be more precise on this. I'm just building it up. The inverse would be something like that. You can define the inverse, but you see, if I take a map here that goes from V to V star, the inverse will be something that goes from V star to V. That's why it changed color. It's not the same kind of object. It goes from different things. Okay. It will become clear, this is robotics, it's called the transpose Jacobian. You know, if you have the Jacobian in robotics, it goes from a velocity to a velocity. If you take the transpose, what does it do? It goes from forces to forces. V star, V star. You see, it's a different thing. Changes color. And here is no problem because you can see that if you can invert the two things, because the transpose basically says writing the M, the VV transpose, or like this or like this, it doesn't change if it's just symmetric. Eigenvalues, well, I told you about this, it makes no sense to calculate. And you know, of course, the determinant, you can properly define in normal case is the product of the eigenvalue, okay, and therefore you can define on the left and also on the right, okay? So matrices are not mathematical objects, okay? This has been known for centuries, and nevertheless, they tell you that they are mathematical objects. Matrices are just a representation of proper mathematical physical objects. They are not, it's mumbo jumbo. What people often do in papers that I've published is mumbo jumbo, numbers, juggling, okay? There are many mathematical fairy tales some told 99% of the time in textbooks, there's a toilet paper than the textbooks. Seriously, because they give you ideas of things and it is not your fault, but people that write those books should know better. Okay. So nullius in verba, you know where this sentence comes from? Okay. This sentence is engraved in the symbol of the Royal Society, the first scientific society in England, where Faraday basically started working as a, you know what Faraday never studied, you know that, right? Faraday was working in a bookstore, finding books. And at a certain point, there was a position as an assistant in the Royal Society to basically help with experiments. And he said, oh, that's nice. He went there. The rest is history, never studied. So, and that is engraved, nullius in verba means don't get anybody worse for it. Okay, so if somebody tells you at a lecture, this is like this, don't trust him. Not because he's an asshole, but because your attitude as an academic should say, give me reason to trust you. And unfortunately, society should learn a lot nowadays on these things, see, considering social media. All right, now let's get a bit more formal, and let's have, we started already 1 hour ago, so let's have a break now.
Some of them will stay for in 2 months.
All right. Any questions so far?
Yeah,
Yes,
just
please.
a quick thing. If we go back one slide to the one that was, I just want to, not that one, the one where we were comparing the two. Yeah. So there is just one thing that I
Yes.
didn't get.
I will get back to these slides after I tell you everything about it, and we will redo it, by the way, anyway.
But just it's the thing that we were saying here about that M goes from is an
V to V.
to V star, but here it's V to V, which
No, it's not V to V, it's VV to V star, and I'll tell you immediately that, and I will formalize it better later. How I define, roughly, I haven't defined, I've been very sloppy, but I define these as a set of linear maps from V to R, right? So if I now give you M as defined there, what is M is defined there is, say the M is defined as a map that goes from V cross, oh geez. VV to R, right?
Yeah.
That's the way it is defined there, okay? So look at this. If I have this M as two arguments, basically, no? I could write M of two things, and I return a real number, right? Suppose I fix one, V, and I leave this open. What is that guy? It's something that maps from V to R, right? If I fix this term, what I'm left is the map from V to R. That's V star. So I can see this as a map from V, that V, namely, V star.
Okay.
You see, so it's the same. So saying that a map is from VP to R is the same as saying that that map is the same kind of object. We'll see this in precisely. I don't want you to understand it precisely now because I will get to that. It's the same as saying that M, let's say this is a map from V to V star. And therefore you cannot calculate the eigenvalue of it.
And that last statement, it's still not.
Because if I give you the matrix, so if, in other words, going back to physics a second, if I give you this work, man, this is terrible. So if I take M and I multiply by V, you get P, right?
Yes.
So this, you see, is a linear map from velocities to momenta. And I told you, and I will be more precise, that momenta are V star. So this element belong to V star. These elements belongs to V. Okay? So this element maps an element in V to an element in V star. So I cannot take eigenvalues because if I multiply this, I get an element which is not longer or shorter than that one. It's a different thing.
Okay, now it's, I
Okay.
connected that. Okay, thank you.
Okay, things will become more clear. I will get much things. But these are simple, subtle things. If you understand one, you'll never forget in your life. We've been talking about 1.5 hours, you know, more than linear algebra that you thought you could have learned. What the hell do not they teach this? That's really something that pisses me off. I tell you that Frederick is now, after fighting, teaching this. And it's been going to mathematicians that teach linear algebra to mathematicians. And they say, it's not important duality. Now you will see in these few lectures how important that is. This doesn't make a difference to make the distinction between V and V star. It's the basic of nature. It's not important. Okay, anyway, I will convince you about that. Okay, so these are the issues. So this multiply, this you cannot do it. The inverse is a different map, etc., etc. But we were at the first of linear vectors and covectors. So now I will start really to tell you what is what, and this. Okay, now vector space. What you have learned of vector spaces? Very likely, unfortunately for you, you have learned that vector spaces are array of numbers, isn't it? How did you learn vector spaces?
I haven't.
Oh, you haven't?
I
Okay,
haven't
that's
had mathematics.
officially. Sorry?
I officially haven't had mathematics.
You are in mathematics?
I haven't.
Oh, you haven't had mathematics better. Yes. You are much better positioned than others. It's much better to learn things right in the first place to dislearn things that you learn wrongly. No, I'm serious. I'm absolutely serious. Okay, so what a vector space is, we should be precise. You know, we've seen what set is one thing we define roughly. I was not precise, but and then we say what a group is as an operation. Now a vector space has two operations, so it's a triple. We have three things. It's not that if I tell you, is that a vector? You cannot say if something I give you is a vector. A vector is only meaningful to be called a vector if you say where it belongs and if you give me two operations. Otherwise, you cannot say it's a vector. So if I give you 3, 5, 4, is that a vector? That's not a well-posed question. The way you tell me is our three numbers. That's it. It is not a vector. Okay? A vector belongs to a vector space. A vector space has two operations. Do you see what I'm saying? Okay. It's a triple, has three things. The first thing is a set. Okay, first thing is a set. And the elements that are called vector if they satisfy the following property. If there is a scalar product, and okay, I should say this is the vector space on R. Okay, so all things we do is our vector space are always based on a field, a real vector space. In quantum mechanics, everything is a complex vector space. Okay, in which the vector space there are infinite dimension, are element of Hilbert space, and are called functions, wave functions. Okay. It's just a vector space, nothing more. Complex, you know, quantum mechanics is very simple. It's just basic linear algebra. Everything is linear in quantum mechanics. Everything is linear, but you should know what is what. Okay, so this is a real vector space. So we have a real now here. If I were talking Kempler's vector space, I would put a C. Same story, nothing changes. We have a scalar product, you see, which I indicated with this thing. It eats an R and eats a vector, and it returns a vector. And it's such that if I take this, you define it in a certain way. Abuse notation. Then you take, and then you have the vector sum. You can define it as taking two vectors and returning another vector. And should satisfy a number of properties. What are called Kani-Adu are a number of properties. I will not spend much time on that. You can find it anywhere. It would, you know, if you go to Wikipedia, you find these properties. Roughly speaking, tells you should be commutative, associative, have a null element, and inverse of the plus. Okay, our operation that you always have in null, and associativity of R with respect to this, distributivity of this, blah, 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 blah. These are what are called the Kani-Adu properties. You can find them. I will not spend much time, but be aware what the way you should define it. But a vector space is not just a set. No, are three things of which the elements, and there are two operations that should satisfy certain properties that you can check. So if I now give you whatever, and I ask you, is that a vector space? Very simple. You just check these things. If satisfying these things is a vector space. So array of numbers, are that a vector space? If you define with the operation and they satisfy, is a vector space. Otherwise, it's not a vector space. Okay. Yes.
A triple is, because we mentioned the group is a set and an operator.
Yeah.
A triple is a set and two
Well, three
operators.
things. Two objects, three objects. So it's just saying to say is a tuple of three elements. That's the way it is normally. Three things.
But that is not related to group.
Well, it is, yes, because some of the properties you have here are actually properties that group satisfy. So in principle, if you take V, for example, vector space with the sum, that's a group. If you only take the vector space with the sum, it is a group. All the properties that the group, so it satisfies that. So indeed, very good question. So I could be much more precise, but I don't have the time to do all theory of mass up to linear system. But it is indeed, I define it separately because of reasons you'll see later. But absolutely, the way you define is like this. You remember this drawing I did. So the bigger one was a group and then the last one was a field. Well, this thing is also a vector. But it's much more than that because it satisfies many more properties with two operations and and that's why it's called a field. Okay. And if this is a field and you satisfy this property, that's a vector space. And then in mathematics, another important things, which is much more relevant for vector fields and other things, is when this is not a field, but it's called a ring. It has less properties. If this would be, you can define things in which this object is not a real number, but it's something else which is not a field, is called a ring. And then it's more or less the same definition, you get something which is called a module. And there's something which is very important for infinite dimensional systems. But that's a different story, okay? But basically the idea, something, if you have a field, real number, complex number, okay, you can define a vector space around it by using groups here and there and having certain properties. That's the idea. But indeed, there's some of the structure is actually a group, but this is more than a group. A vector space is a bigger structure than a group. Yeah. Okay. Very, very, very important. There is no way in a vector space. We do not have this. We have no inner product. We have no orthogonality. We have no length. If you see a book that tells you that vector space is something which vector have a length, use it as toilet paper. It's not true. It's an extra structure. It's what sometimes is called, satisfying certain property, a Hilbert structure, an inner product. The Euclidean space we live in, okay, if we take a point as an origin and we can use it as a vector space, then we have an inner product orthogonality because we have a certain operations extra. In general, you don't have that operation. That is a metric structure that you have, which is, for example, what in general relativity changes depending on mass and stuff. I will actually show you as an example Einstein's field equation. Once you understand what tensors are, you will understand it like this. Okay. So be aware, if I give you a vector space, you have no length, you have no orthogonality. Okay. This seems details, it's absolutely extremely relevant later. Okay. Well, errors emanating from common point, you know, you can define an operation, it's called of sum, it's called the parallelogram rule, and what you learned the first time you played with lines and vectors drawn on paper, kind of thing. Yeah, you don't need any coordinates to talk about that. You can define graphically the sum of vectors, right? You don't have any real function on an interval. Well, if I give you an interval and I define a function on that interval, you could check all the properties because I give you a function. Can you multiply a function for a real number? Sure, you get a bigger function. Can you sum two functions? Sure, pointwise you can sum two functions. So the set of functions in an interval, okay, is a vector space. Is it finite dimensional? Well, I haven't defined it yet, but you will see it's not finite dimensional. Okay, but what you know Fourier, right? If I give you a function in an interval, what do you know? How can you write that function? How can you write, if I give you a function on an interval, what do Fourier tell you? What you know? You can write the Fourier series, right? Because it's a periodic thing. So you can say, well, you take that as a period. You don't give a shit what happens there and there. You can write it and it will repeat itself somehow. Okay, but you can actually write that function as an infinite series, which is called a Fourier series. Okay, what does that mean? It's a series. Aha! How many elements are there? Infinite. Are they countable? Yes, they are, right? Because it's a sum. It's not an integral. It's a sum. Oh, it's an infinite number of sum. Aha! Oh, wait a second. But isn't that kind of orthogonality between this sinusoid? Yes, there is an inner product. Aha! That's a Hilbert space. Is a what is called in quantum mechanics a separable Hilbert space, in which the number of bases is infinite. Okay, it's an infinite but countable. These are all concepts that actually will pop up. Okay? But it is a vector space. General fields on space with scalar multiplication, yes. If in case you have functions as a multiplicating factor, then it becomes a module. That's a different story. I will not talk about that, etc. Anything satisfied in the requirement is a vector space. Now, use that bloody abstraction. You know, vector space as an outer array of numbers. There's just one kind of things you can give it a structure of a vector space. Okay, so when you think about vector spaces, think about try to learn yourself to think in an abstract way. Okay. Now, what are, if I ask you, what are now maps between vector spaces that preserve their structure? What would you come up with? I know you know, so you don't say that. For those who really don't know it, what would you think? You want to preserve the structure. What does that mean? That if I have two vector spaces, I have a map between these two vector spaces. Then I have a vector space, we have a vector space there, whatever they are. They can be finite, infinite dimensional, and no problem. It's no problem. One of the two can be finite dimensional, one can be infinite dimensional, both infinite dimensional, etc. So if you have that map, what do you want that it preserves?
Two operations that do happen here have to result in the same thing there.
Very good. Okay. How would you call a map like that? If you take a linear combination here, you map it there, you get the same linear combination there.
Again, a homomorphism?
No, it's more. It's a map that's where superposition works, right? You take a linear combination here, you get a linear combination. What is it called, that map?
Isomorphic.
No, it doesn't have to be an isomorphism because this could be finite dimensional, this infinite dimensional, the other way around.
Linear.
Ta-da! Very good. It's a linear map. Okay. So maps between vector spaces preserving the structure are called linear maps. That's it. What linear maps are structure preserving map between linear spaces. I don't care if the linear spaces are finite dimensional. I don't care if they're infinite dimensional. That's what it is. Okay. Could you give me an example of, well, I don't want to go in such detail. It's an exercise, okay? But think about this. If you take an interval, you've heard about the Dirac pulse, right? Which is defined in very mystical way, you know, forces that you have had. Okay, is that a function? That's not a function. It's called a distribution. What is a distribution? It's a linear operator on functions. If you see it that way, you take an integral in the way that's normally defined, okay, then you see that the delta together with the integral belongs. If you take a function as an input, you get something which is out. Linear map, linear integral, linear operation. And not only in that case, if you take the integral, is a map between what? Infinite dimensional space and one dimensional space. It's the result of the integral. No problem. Okay. So you see, this concept is very strong. And now you can think about linear maps in a much broader sense. So linear operator in quantum mechanics are just infinite dimensional. What's the big deal? It's a linear operator. If I give you a function to this linear operator, then you return another function. Okay, and in quantum mechanics, these operators are the base of everything. the observables are operators that satisfy certain properties, are just linear operators. Actually are endomorphism, so it's a map from a space to itself. You can calculate the eigenvalues. Okay, and these are the observable values that you can get in quantum mechanics, for example. Okay, but that's what they are. Just linear operator is a map from vector space to vector space. All right, so this is the definition, right? You see, this is the definition of superposition. Okay, so it's basically a vector space on the left and a vector space on the right. You see, I explicitly write different symbols for the operation because they're not the same operation. This is a different set with different operations. Okay, this is not just because I want to make things more complicated, because this is what's happening. No, this could be complex. It can be something. No, it's not true. It should be a real map, but could be something very funny, but based on the same field of real numbers. This based on the same field of real numbers, and this is satisfied. You see what I'm doing? I'm taking a linear combination on the left, and I want that if I map single of these elements on the right, and then I take a linear combination on the right with the same coefficient real of the linear map, I get the same thing. Isn't this identical as what we did with groups? Yes. You know, it's obvious. You could have told me what that would have been, right? So you see, a linear map is nothing else than a structure preserving thing. Do two vector spaces need to have the same dimension? Of course not. If they do, okay, do they have to, are they isomorphic? No, it's not true, because they need some conditions to be met. Once you have a linear map, what are things that you can say about linear map? You can say, for example, what is a special element of a vector space? Its origin, right? So things you can ask is, how many of these elements here map to the zero element here? And then we'll see this thing's a subspace here. It's called the kernel of that linear map. Okay, and if the two things have the same dimension, the kernel is zero, you imply is isomorphic because they have the same dimension and you can map one to the other, etc., etc. All concepts used daily now will frame that in a proper setting. Okay. Basis. Okay, now I've been abstract, didn't put any coordinates. But I sometimes, especially for engineer, coordinates are useful, but you should only use them if needed. Okay, not just use the coordinate and forget about that, use coordinates. Because if you're doing proper engineering and proper physics, your coordinate choice should not matter. Things should be invariant. Okay? So a gentleman only chooses a basis if he must. Okay, so if you don't need, don't use it. And to be gender balanced, okay, a lady must never go to the cemetery. You know what is the cemetery? A matrix of numbers. Okay, so you should only use matrices and therefore choose coordinates or a basis, we'll see, only if you really cannot do the calculation, understand the concepts without having to make that choice. And then you should check if that the results you get is not dependent on the choice you made. Okay. Now, what is a basis? If I give you a vector space, okay, then I can take a set, which is a subset of the vector space, and if every subset of that set is linear independent, what does that mean? Well, you know what linear independent means, right? You take these things and you can express one as the other. And B generates V. So it means that you can take any element of V is basically the result of a linear combination. Excuse me, any element of V is a result of a linear combination of element of B. Okay, that means the B is generating V. That's basically what it is. Then that is called a Hamel point. Okay, and for infinite dimensional system, there is another definition which is called Schauder basis, a different thing. But this is what is important for us because it can be proven formally that if B is finite, okay, and therefore there are n elements of the vector space that generates everything, okay, then you could prove it any other subset that does that has the same number, and that's called the dimension of the vector space. And this is true for finite dimensional. And if that's not the case, that is called an infinite dimension. So what we normally will work on would be finite dimensional, but functional spaces are infinite dimensional. Vector spaces, you can do the same. And if you go to numerics, for example, in numerics is very important when you want to basically do calculation of fields, electromagnetism, of things like that. You use, what are called finite element models. And finite element models basically define the subspace of the infinite dimensional space, which is generated by a number of functions, which are polynomial or other kind, that are basically their representation that you use, and you will commit an error, of course, in your numerical things, and all these things can be framed here very nicely. Instead of being very superficial, once you understand this, I could draw you a diagram that you understand precisely what finite element models is. Okay, and I may actually do this during the course. Okay, now we will restrict to finite dimensional. Any questions? Yes, please.
In the previous slide,
Yes.
you said that V is every element of V is produced by an element of by
A subset.
a subset of.
Yes.
Can you give me an example of that?
Yes, it's a vector space. If, for example, well, Fourier, as I said before, if I well, it's not finite, that's an infinite dimensional, precisely infinite dimensional case. But for example, in an interval, if you have Fourier, there is not a finite subset that it generates the function. It has to be an infinite series. Okay, so it's an infinite dimensional in that respect. But if you take any vector space, like for example, R3. So if I give you any, so this is the origin. I define my vector space, all the line that go out of this and go to any point, for example, like that, and I put an arrow, okay, and then I define a sum as a parallelogram rule in 3D, and I define a multiplication by a scalar by saying, well, if the scalar is 2, you take these twice in the same direction. There's no length, I just say twice the same direction. There's no length, okay, and this kind of thing. So that would be a vector space. Well, it's clear you can choose 3 vectors which are linearly independent, and you can generate any vector as a linear combination of these 3.
Okay.
That's it. Okay. Okay.
Yes.
Any other questions? All right. Good. So now we restrict to finite dimensional. We will lift this hypothesis when we possibly go to fields, because everything you learn, everything you'll see on port is generic. It works finite, infinite dimensional, even quantum cases, etc., operators or whatever. Important notation, Einstein summation convention. So if I write then a bunch of numbers, you will see, I will recall this. If you see something like this, this has 6 indices. Okay, 6 indices. So it's a bit bigger than a matrix. A matrix has 2 indices. Okay, that's what's called a second order tensor, as we will see. These are 6 indices. In physics, you have things with a lot of indices. Okay, curvature have, for example, the Ricci tensor. The curvature tensor has 4 indices, for example, etc. But when I write these indices, it means that there is, and implicitly the dimension of the space. So, for example, in our case, suppose it's 3. So you know that all these indices can be 1, 2, or 3. Okay, and you can calculate how many real numbers there are in these combinations and do a bit of combinatorics, right? Okay, so all possible things, depending on the dimension of the space. For example, in classical physics, you have 3. In relativistic physics, you have 4. We have time as 4 dimensions. Then, if I write 2 indices with the same letter, what I actually mean is this. I don't draw the sum. Okay, I basically am saying that I have then only 4 independent indices. The other 2 have been contracted. That's the definition of contraction. Okay. An example which is simpler is this. If I give you now a matrix with an index up and an index down, which is very different than a matrix with 2 index down and 2 index up, we'll see what. That's exactly the difference between this V and V star. You'll start understanding why that is relevant very soon, okay? But if I give you 2 indices, 1 up and 1 down, otherwise I cannot do. If I take 2 Ks down or 2 Ks up, that's called bullshit. You will see, we will define bullshit properly, okay? But if you have 2 indices, If you are, because of course you can write it, but you can mean something else. But if you are consistent with this notation, you can never take the sum of two indices down, two indices up. Can only be one up and one down. And you'll see what I mean with that. Now it's just a notation issue. Is actually what I mean is this. So if this is a matrix, what does that mean? That's called a trace. You just take the sum of what? Of the diagonal elements, right? 1, 1 plus 2, 2 plus 2, 3. You know what's funny? Because when I study, this operation and you're given this stuff and you say the trace, and I say, what kind of operation is this? Why would it be relevant if I give you a complete matrix and you just take the sum of the elements and you just discard the rest? What doesn't make any sense? But it turns out it makes a lot of sense, much more than taking eigenvalues of a matrix that you cannot take eigenvalue of. And I'll show you. Okay, in quantum mechanics, the trace, for example, gives you the probability, the univariance of probability, etc., etc. Yes, please.
So this is basically a way to, if you have a really, it's not like a matrix, but it's a space, I guess. You can sort of take a line in that space, define depending on where you set these.
No, it's more complicated because if you give you a matrix, you can take a trace only for one index up and one index down, which you will see understanding that only for those objects that are linear operator. So you could also take the eigenvalue of that object, would make sense. Okay, because the way you would write, well, I can give you a pre clue what is going on here, because basically, and this is Einstein's notation, if I write an index down or an index up, it will tell you immediately if that thing is a vector or a covector, V or V star. So if I give you a vector, in the previous case I had here on the board, I will write an index up. But the P, which is a momentum, which is a covector, write an index down. Just by looking at this, I tell you immediately, this is a vector and this is a covector. I will define it properly, but this belongs to V and this is V star, as this guy mentioned before. Okay, so now if I give you the example I gave before, which was M, oh Jesus. If I have P, M was equal to P, remember? Okay, and I told you V was a vector, right? So I would have an index here. And I told you P was a covector. No, this is new. J, okay? Now look at this. I'm doing a matrix multiplication here, right? Look, this is J is down, right? So this comes from a J here. There's an I here. So there's an I here. You contract these two like that, you see? So what I recognize here, that this of course is a matrix, has two indices. I immediately recognize that this object is not a linear operator. Because if it takes the vector, it spits out a covector. I will be more precise on this. But instead, if you do the things of eigenvalue, if I give you an A, which is a linear operator, what does that guy do? Well, it takes a vector, okay? It needs to be multiplied, so there must be an index here it contracts with. And what does this spit? A vector, right? So it means that the under index should be there. Now very vague. I will be very precise, but this is the notation, because now you see, if I need you, this is two indices, so it's a matrix. This is matrix, two indices. But just by looking where I put the indices, I tell you immediately what kind of object it is. Because if I see that an index is down and an index is up, I know it's a linear operator. I can take eigenvalue, I can take the trace. It doesn't matter in what coordinates you do, you always get the same results. If I do it here, you get bullshit. Okay, so you see, it's a way to immediately recognize what kind of physical object you're dealing with, and what you can and what you cannot do. And if I do, for example, kinetic energy, it works. Look, if I go to kinetic energy, energy is equal to half. How do you calculate kinetic energy? M Ij Vi Vj. You see? Boom, boom. I didn't write the sum. There is a sum here. I didn't write, but implicitly there are some of I and j from 0 for 1 to 3 or whatever that dimension is. This is Einstein notation. I say I, there is a sum here I didn't write that sums from I from 1 to 3 and j from 1 to 3. Here only I, because j is left. Okay, so that's the thing you will see. Here's the notation I actually indicated here. So 5 minutes to go. Now we've defined formally what V star is. Now, R, real number with a plus and multiplication in the way you use it every day, is a vector space. So I can define a linear map. I can consider linear maps from any vector space to R with operation plus and times. Okay. And if that is a linear map, okay, I will call that a linear functional. Okay. Now, for this, if the vector V is finite dimensional, that will be an array of number. If you take a base, we'll see. Okay. Just for your intuition, I'll be precise. If I give you a vector, choose coordinates, I get, and I will define this formula, I get an array of numbers, right? Vertical. If I then multiply and I want to have a map which is linear that goes from this to a real number, what do you get? What do you use? It's a matrix which is high 1, right? You multiply. Okay. Well, this is a velocity, this is a force kind of stuff, and this is power. Yeah, I will be more precise on that. But this could be also infinite dimensional. That would be an integral, for example. If you have a functional space, there's a function, this linear operation could be a Dirac pulse, and then if you have, and that would be a linear functional. Finite dimensional space, infinite, doesn't matter. So something that maps from a vector space to a real, to the field, and the operation that belongs to that field is called the linear function. And, you know, is what it's again supposed. So definition, and then we could more or less conclude with that. V star are called covectors or dual vectors. It is also vector space, okay, but is not the same vector space as V, okay, and it is the set of linear operators from the vector space V to the real number. That is the definition of the dual vector space. And it is important, I have not defined the basis, but what you can immediately see, and it will become clear later, if I give you a vector space which is finite dimensional, you remember I said, you know, if it's finite dimension n, I can choose n elements in that space, which will generate the vector space. So I take linear combination of these, will give you any other vector. Okay. So if I now say, if I have a space V, okay, which is dimension n, it means that I could choose n linear independent vectors, okay, and then I could generate any element here as a linear combination of these, right? Well, it turns out that by definition, by that construction, there is a uniquely defined dual basis, which I write it like this. You see the indices are up now. You understand the details. I'm making this distance. One is dual to the other. These indices up are n element in V star. For finite dimensional, you can show that the dimension of the dual space is the same. Okay, so if V as n dimension, the V star as n dimension, that there are n elements that satisfy this condition. What does that mean? Well, this means that, you know, what are these elements? By definition, these are in V star. What are elements in V star? Are linear operators. So I can take them as linear operator on element of V. Oh, but these are elements in V. So I can write this. Okay, you see that? These elements are in V. It's any vector. So, and these elements are in V star. By definition, is a function from V to R. And this symbol is called the Kronecker delta. It basically says, well, this is 0 or 1. If the two things are equal, is 1. If the two things are different, is 0. Okay, you will understand what that means, but this so far you know. And this is a notation, and it basically says this. And this is what Dirac, for example, uses a bracket notation in quantum mechanics. This is a vector, this is a covector. In quantum mechanics, you may have seen things like this. Schrödinger equation, something very mystical. Well, the first time I saw this, if you look at Schrödinger equation in quantum mechanics, is this. Yeah, you have Hamiltonian, and then you have this is Schrödinger equation. How do you understand Schrödinger equation? What is this? This is a vector. What is this? It's a linear operator. It's called the Hamiltonian operator. What is this? Well, it's a time derivative of this vector. Complex number, reduced Planck constant, Schrödinger equation. Okay? This is just the way, because Dirac said, okay, this is a vector, this is a covector. What are called? These are called brackets. And Dirac said, this is kind of humor, mathematical humor. This is a bra, and this is a cat. Bracket. Okay? So this is a vector, it's the way that Dirac was showing. Now the point is, you have that, and then I will start from here and explain you what this precisely means, because it's a bit abstract now. But basically is if I give you a vector space and I choose a basis, and in that base, for example, you get a vector like this. Suppose it says 4-dimensional, let's not exaggerate, 3 dimensions, make it 3 dimensional. Suppose that I give you an abstract vector space and I choose 3 bases, E1, E2, E3, this guy, n is 3, E1 is 2, E3, okay? And then I say, well, this times this one in that base is basically give me E1. Okay, that's what I mean. So this is a numerical representation of E1, and in that base, and this would be the numerical representation of E2 in that base. Okay, and this one would be the numerical representation of E3 in that base. Now, what about the linear operator? Well, it's very easy, because if I write them as row vectors, okay, this one would be this guy. Okay, and then this one would be, well, not written, but the second guy here and the third. Clear, right? So that's as simple as that. And we'll start from next time in that way. Any questions? No? Yes, please.
Is there anywhere where we can get this also to read?
Yes. So there is.
So we can review it a little bit in our own
Yes.
speed
So
as well.
there is, if you are very serious about learning it, you know, the absolute best possible place you can, the lecture, the video lectures of Friedrich Schuller, and there is also some written material about that. But it's very, very extensive. It starts to tell you what propositional logic is and defines it in a proper mathematical way. So it's kind of chewing, but it's, you know, Friedrich says my course is done for zero knowledge and infinite intelligence. So, but it's very precise. You can understand it without any doubt, but it's, there is actually for the course, the MDK, Vasilis has been writing a lot of material and it's very precise. So that is definitely something you could read. And that's the material we give to the students of the course. So that is something, it's on the canvas. I should download it. Maybe if you cannot access it or make it accessible for all of you, that's also a possibility.
Put it on the cloud.
Yes, and of course, this is, I'm not doing fancy mathematics now. This is very basic mathematics. So Wikipedia, you can find everything. But now, at least to have critical eyes. Now you can see, you know, if they are correct, because duality is something very important. And there are a lot of things that, as I said, are not precise. And Wikipedia usually is very precise on these things. But now you have critical attitude. Okay. Any other questions? So remind me, I will open up for whoever needs Canvas, and you can download these things.
We are also trying to build a website where to gather all this material for
educational purposes.
Oh, yes, yes, for you, Robin, Karen setting up a website where all these things can also be.
There will be also these vectors and well, I'm working on building all like documentation, so also notes and so, but it will take some time.
Any other questions?
I have one, but maybe it's for the next time, but I can just,
Everybody who needs to go, please feel free to leave. I'll stay here if there are questions or to answer any questions, so.
yeah, so far, when we defined the vector, we said a vector is, or a vector space is defined in this particular way with the set and the two operators.
That's correct. So,
Right.
well, it's something, are three things that should satisfy this property, yes.
But we never, and if I think about vectors in that abstract way, there is no reason to, there is nothing that says that a vector has to be written in this way or in this way.
Absolutely. Very, very good comment. Very good comment. There are some bad books that tells you that things you write like these are covectors, things you write like, it's not true. This is just now for giving you the intuition. You know, if I write it like this, or write it like this, is not that the nature of that thing changes. Okay, it's the same thing. So it doesn't matter. It's just a convenience way of thinking about it.
Okay, just because when we were writing the covector, I felt that this is something that we.
No, let me tell you, this is red. If I had some other colors, I would have done this blue. Are different things. Where the colors does matter here. Okay, which tells you there are two different spaces. Okay, but I didn't have the color functioning, so we need really to get something working here. But these are this is very different than this. Is not the same guy, not because I wrote it like this. Okay, but you know, let's try. This is whatever. You know, if I turn it, this becomes.
Yeah.
It's a different thing. Okay.
So as a vector,
Is the bad guy?
so a vector and a covector are two things that when the linear operator operates on the vector, there is a way which this is defined how it's done. It doesn't matter how we write it.
Yes, precisely. And it turns out, and you will become clear that you can see it. So by definition, I define that a covector is a linear operator from vector to a real number. Okay, very clearly force, velocity, power. Okay, that's the physics around it. And actually that would be the port. We'll see that. Okay, but you could also see the other way around. If for finite dimensional is always the case that a force is a linear operator from velocity to power. But you can also say a velocity is a linear operator from forces to power. Same story. Doesn't matter. The point is that you have this thing, which is the natural pairing. So if I give you a velocity, if I give you a force, they kiss each other and power comes out. Okay, but they come from two different worlds. One is from Mars, and the other is from Venus. Okay, but they are very much related. You know, it's like a man and a woman, and power comes out. But they are different. That's the point. And that difference is not made. In linear algebra, the difference is not made. And an uncountable number of bullshit is coming out from research and other things where it's really conceptually wrong. It's not just, it's not mathematically precise. No, it's conceptually, physically wrong. So you need to make this distinction. Yes.
So clearly duality is important. So what's the main argument behind the people that are saying that it's not relevant?
Because they don't understand the thing. Seriously. Because they don't understand the thing.
Isn't like the normal way to teach this mainly based in not thinking about the physical world, but more about the numerical world in pure term of coordinates?
We are engineers, right?
Yeah, but like
we are dealing mostly, I think, with
like
physics.
Mathematicians that aren't engineers.
Mathematicians are the one that actually told me how to do this stuff. Okay, so it's bad mathematics. You know, doing linear algebra while making this distinction is seriously defendable bad mathematics. And that there are mathematicians in our university that actually answered to Frederick that was not important. Sorry, but I would say they do not belong as professors at Mathematical Institute in a university. That's just my opinion. I can tell them straight in the face. unless they realize what they mistake and they study this stuff and they teach it properly. Because you can verifiably, and I will see it in this course again and again and again, how that's important. It's absolutely fundamental. If you give me mumbo jumbo numbers and you take like this, you know, you can play with number and you can invent whatever in your fantasies, fine, it's your right, it's a free world. But if you want to use mathematics to do physics, well, engineering, which is based on physics, it's a different story. Even if you go to information, which is, you know, very abstract, but it turns out I'm realizing right now that information is even deeper than in certain things in physics. Even there, duality is important, because probability and information have a concept of duality to preserve something. This is so incredibly important that the more I use this stuff and I understand it and chew it, the more I understand how important that is. And it's just, no, we don't teach it. It's disgrace. Yes.
I just have a question.
Yes.
Is it correct to call Euclidean norms linear functional, since you said
it's a quadratic function? So look at Euclidean norm. We'll see this very much in detail.
Linear functional.
It's an object like the M. That's like the M. The Euclidean norm. Well, it should be more precise. So what is a norm? A norm, take a vector and gives you a number satisfying certain properties. Something with the norm satisfying certain properties is called a Banach space. Okay, in finite dimension, everything is easy. In infinite dimension, you have to be careful because there are holes in space and stuff like that. And if you're interested, I can tell you more, but that's not the point. Something, if you have instead of give you a norm directly, I give you an inner product. What is an inner product? It's a matrix with two indices down. Because if you have matrix with two indices down, I give me two vectors. You can contract them, one up, one down, one up, one down. Okay, you can do that. Okay. Then you have an inner product. Then you can take the square root. If you take on right and left the same vector, and you take the square root, you get a norm. So if you have something like an inner product, which is called the Hilbert space, where these guys belong, because you know, quantum mechanics tells us that is vector space, and there is an inner product. Okay, then you can define a norm. But if you have a norm, you could define an inner product that's called a parallelogram identity in a certain way. But the normal way, in natural way in physics, is you have, and in manifold, this will become even clear because all physics and mechanics is based actually on what's called the Riemann geometry, which basically gives you in each point a quadratic form, which is the inertia in robots, right? In each point, you have that is, then you have a norm, but it's an extra structure. Otherwise, you cannot talk about norm. You cannot talk about inner product, about nothing. Okay, so it is really a quadratic form that you will see. I will introduce that. Yeah. Yes.
He said that a lot of these calculations that are being done in those labs require extra parameters to be true for that to work. So if in the book we can write within these certain parameters, we will take as given these certain parameters, and then we teach you this branch of math, and then you can go and understand this duality later. Would that be acceptable?
No. I tell you why. It's simple, because if you first in academia, you should be critical. So why do you choose certain coordinates? I'm perfectly fine if you say, you know, I choose these coordinates and we work with that. But you should tell me that your choice is not preventing to make mistake. Okay, so you tell me that everything you do is what it says, coordinate invariant. That all the operations you do are independent of your choice. If you assure me that that's the case, and that's called tensor calculus, that's exactly what we'll start doing next time. Then I say, okay, that's fine, because you know these things, I wrote it like this. These MMIJ are matrices. I'm not saying that matrices are useless. Matrices are a very useful thing, but it's just a numerical representation of an object which I now know to represent to understand what it is, so that I can say, oh, I can take the eigenvalues, yes, no. I can take that, yes, no. I can multiply, yes, no. Because if you remember this square, for example, if I give you MIJ, and I give you another Mij or whatever KL, can I do something? No, they are all the indices down. I told you it makes no sense. But if I give you a Ij and I give you an IKL, oh, I can contract these two indices. So let's call this also K. What I do by doing calling K, I basically put the sum here, which is invisible from K that was equal to 1 to 3, square of the matrix. And then you see these are all matrices. But now I built in, and this is what I was saying, you know, units are important, you check. Now, on the basis of these indices, you see what you can do. If I give you these two things, you say, I cannot do anything with two objects. I need something else if I want to do something with these two objects. You need something that has, for example, I don't know, two indices up, Li. Oh, okay, and then I'll contract this with this, that with that. Okay, I can do something. You see, you recognize you need something else to do something. If I give you two vectors, Vi, Vj, I can't do anything. What do you need? An inner product, a quadratic form. Aha, now I can do something with it. It guides you as units check. This guides you what the object you're dealing with, if you can do anything with it. It tells you straight in the face what you can do, what you cannot do. So it's really something very, very powerful. And what do you think what Einstein did? Einstein, you know, recognized the geometry, and then at a certain point says, well, you know, I need to have this tensor. What can I do? There's this tensor there. And he said, well, at least from a tensor point of view, that makes sense. And eventually he said, oh, this works out. That's the way it works. Okay, if you have it in general relativity, it's basically Einstein field equation. Like this. That's Einstein field equation. What does that mean? Well, this is a tensor, two-order tensor, kind of big matrix, 4 by 4. This is a 4 by 4 matrix. This is called the energy stress tensor. I didn't tell you anything, of course, right? But now I tell you what this is. Well, this is basically, if I remember right, IKIL. This is called the curvature tensor. You see, I contracted this too. So this is an element like this. Okay. And there is something like the Ricci tensor here. And then you have a G. I remember, if I remember right, oh no, here's the G. IL, and then you just built it right, and I don't remember the details, but I could find it out, and then you have this element. So you see, all the indices are right. Contraction, this with this, this with this, and eventually you are left with only two indices down, which is called the Einstein tensor, which is based only on curvature and the matrix of space. And this is another tensor, which is based on the amount of energy over a certain point of space, which gives you the curvature. Okay, it's all based on these things. You will not be able to understand it like this, I guarantee you. Any other questions? Okay, all right, see you next time. I don't know when it is, but thank you.